Hi, I am so excited to be introducing Dr. Hsin-Liu Kao from Cornell today, who directs the Hybrid Skins Lab and is an assistant professor of human-centered design. I feel like I'm very excited about her work because of how she thinks about embodiment and digital fabrication, and I can't wait to hear more about it. So without further ado, Dr. Kao.
Thank you. Well, thanks so much, Crystal, for the invitation. And it's great to see you all here. The last time I was back was sometime last year, but I was only here under 20 hours. And so this time I actually had the opportunity to walk around Kendall Square. I used to live in 100 Memorial Drive, which is like 5 seconds away from my lab, the media lab, and it is completely transformed. So this was very exciting for me to see how MIT is, transforming. And so I think it's really a pleasure to be here to talk about my lab's work. So I am currently a assistant professor at Cornell University, where I direct the hybrid body lab. And we are a really transdisciplinary research lab that focuses on thinking about the design, engineering, and creation of, I would say, materials, processes, and also tools for crafting technology on and also into the body surface. And the lab that I lead, we really have a team of researchers from all different disciplines. And I hope to also, through my talk, to really illustrate, I think, really the importance of transdisciplinary work to tackle some of the pressing societal issues that we are really facing today. And today, the lens that I would like to use to introduce my lab's work is thinking about designing hybrid skins. What we are seeing here are two seashells. However, these are not seashells that are only made by Mother Nature, so found in nature. They've actually also been crafted by the human hand more than 40,000 years ago to be worn as jewelry, to decorate and adorn the body. So I really believe it's a very, very innate human desire and fascination to use the found materials around us to alter our physical bodies. Here, I am showing some examples of ways in different periods in time and also across different geographic locations and cultures throughout the world, right? In which people have used the materials around them to craft and alter the appearance of their physical bodies. And so really by decorating, by changing the way we look, we really do construct our identities in ways in which we would like to present them, right, to the external world. And we're now at a very interesting place and time in the history of technology. And so I was also just really blown away by the MIT Museum, and especially looking at the history of computing. There's like a core memory, a woven core memory, which is kind of related to my research. I was nerding out a little bit, but we're at a very interesting place in time where hardware has become miniaturized to an extent that we can also start looking at it as a material for crafting and constructing our physical identities, right? And this also includes not only hardware, but also a lot of breakthroughs in novel materials and material science. And a lot of the exciting research is happening right here, right, at MIT, amongst all places. Um, this realm of what I like to call epidermal electronics, on-skin interfaces, conformable wearable this is a very new field, starting in the early 2010s. So a little over a decade, right? This field of research. A lot of the initial research, of course, originated from the material sciences. And of course, with a very important focus, right, on figuring out, right, how do you actually make sensors that can go on the skin surface, right, and be wearable and durable, right? So technical breakthroughs. However, anything that is worn on the body, right, is inseparable from the greater and broader cultural and social context, right, in which we are situated, right? And so in my lab's research, we're very interested in thinking about how in creating and designing the next generation of conformable on-body technology, we can create them with a greater connection and dialogue to the greater culture and social context, right, of what it means to start putting physical devices on and into the skin surface. We really think that technology and culture, in terms of thinking about these two lenses in designing for the body surface, I really like to see them as not contradictory forces, but rather that they are two lenses that are very important to inform and build each other up, just like a spiral staircase, right? And I like to call my work hybrid skins and our investigations in creating these hybrid skins because these interfaces, they often have purposes that are, of course, technical and functional. However, by being on the surface of a human body, instead of being on the surface of, let's say, an object or a table, they have intrinsic, a very tight coupling with cultural, social, and even, as we know, political considerations. And so I believe these are two very important perspectives to take together. I really love this quote by Cynthia Wilson. She is a culture critic based in New York City. She's written a lot of work observing what Americans wear, basically, through different periods of time. And so she says here that your style is your visual interface with the rest of the world, right? So, and this word interface, right? It also has a very special meaning in human-computer interaction, right? It is really how we intersect as humans, right? With computing, with machines, right? And the interesting thing about interfaces that are on our body, I really believe, is that they often encompass our social, cultural, and even political identities. And so today, in this talk, I would like to talk about a couple of different suites of projects in which we think about how to create more culturally curious, more culturally inquired hybrid skins. And the first line of work really looks at thinking about more culturally inspired form factors, okay? And a lot of this early work began when I was a PhD student here at the MIT Media Lab. And this project, Dual Skin, was initiated in the early 2010s. So in 2011, the epidermal electronics science paper from John Rogers' team of material science came out, and it really ushered in tremendous interest, right, in engineering, material science, thinking about designing these interfaces. I became very interested in thinking about how to connect them, right, with existing ways in which people are already decorating and crafting their body. So there is a reason, right, to wear these devices. And at that time, there was a very, very popular body art trend called flash tats. Please raise your hand if you have heard of this. Oh my goodness, like the number of hands raised has improved. I remember like 7 years ago when I gave a talk at MIT, it was desert silence. People were looking at me like I was crazy. But yeah, so these are basically temporary tattoos that I believe we've all played with as kids. However, because they were printed with gold or silver ink, so they had this very jewelry-like aesthetic that made them very popular. So even Beyonce had her own line of these flash tats. So it was a big thing. And looking at them, I was very interested in thinking about how we can create a fabrication approach to enable anyone who was interested, right, to also build a on-skin interface so that they could designate, right, how a smart tattoo would look and also what it would do. And so dual skin is a fabrication approach using a off-the-shelf material of metal leaf. This is a very inexpensive material that you can get in any craft store. And you can create a few categories of devices, right? From, for instance, touch sensors, as we can see here. So I think some of the human-computer interaction modalities, displays, right? And of course, also thinking about wireless communication and also more decorative purposes. And so after this project, I was very interested in thinking about how we can increase the complexity, right, of wiring more complex sensors on the skin surface. And I think for anyone who's worked with textiles or soft interfaces, we can understand like, wiring and then streamlining the wiring is always a major challenge. And so in this project called SkinWire, I got very interested in thinking about how we can move a one of the most complex on-body sensing interfaces, namely the hand gesture interface in the wearable computing field, which typically comes in a glove form factor. And is often quite bulky directly onto the skin surface. And this was also a project that I conducted in collaboration with Technicolor Research when I was an intern there. And they were very interested in also using it for, just hand gesture motion tracking and I don't know, like movie settings. And this project actually took a lot of inspiration from wire-based hand art. Please raise your hand if you've heard of wire-based hand art. Nadine, yes. Okay. So I have one of my fashion design students from Cornell here, kind of like, So this is a very interesting type of body decoration that's, I think, still quite popular in which people take wires or threads and as a decoration, they place it directly on their fingernails or even their face. You can see this in some fashion runway shows, right? And I was just really interested in thinking about this potential, right, to really streamline these complex wiring in a much more accessible manner by taking inspiration from this body art. So what you can see here actually has around 20 wires in this image on the right. But because of this fabrication approach that we were able to introduce, we're able to fully streamline it into a fully self-integrated hand gesture interface. And so in the prior two projects, we demonstrated applications on the body, right? And just as someone who wears makeup, I know there's some folks here as well, right? I was always very interested in thinking about putting technology on the face, right? And what it means, right? And so in this project called A Slucent, the student who led this project, Elle Lowe, she had the daily habitual practice of wearing eyelid stickers. Please raise your hand if you've heard of eyelid stickers. Very good. Okay. So these are, a type of body decoration more popular in East Asia. When you put it on your eye, it can increase the shape of your eyes, right? And of course, there's like, cultural reasons and debates we can go into for their adoption. However, we saw it as a interesting modality, right, to add sensing capabilities to the eyelid. And so this is a capacitive sensor that can go in the crease of your eyelid and it can detect eye blinking motions. And through some machine learning, it can then infer activity through your eye blinking. So this is also just a really interesting, I think, form factor for us to examine. I was also very curious to think about form factors that are much more organic, right? So the prior couple on-skin interface works come in still more of a layered skin overlay form. However, if we think about the things that we put on our body on a day-to-day basis, they often come in more organic form factors such as gels or creams. And this project Skin Morph was really inspired by the gel-based form factor, and to think about whether we could create programmable gels in a way that they could serve as as I like to call it metaphorically, a interactive wearable armor. Okay, and this was really enabled by the material design of these smart hydrophilic gels. So these gels, when they are in room temperature, okay, they're soft and clear. However, when they become heat activated, they become stiff and opaque. And this is a reversible interaction and therefore programmable. And we created a couple of applications thinking about designing skin as armor. Okay, so here we can see an example of a carpal tunnel glove that is able to map to the individual's pain profiles, right, and to adjust accordingly based on the person's motions, right, and also thinking about tunable protection for high impact activities such as hockey. It's a very popular sport at Cornell. So thinking about this potential, right, to design a second skin layer that is tunable in its rigidity and stiffness. And so after looking at some of these examples of our approach in creating more culturally inspired form factors that are situated on the body surface and on the skin surface, we're also very interested, right, in thinking about kind of I would say this interesting boundary, right, where devices are on the body, but kind of going inside the layer of skin itself. And I like to call this next suite of projects in skin interfaces. So they're really thinking about how we can detect things that are secreted from the layer of skin itself. And to really straddle this interesting intersection, right, between the skin surface versus moving inside the body. Okay, and so are the biofluids, right, that our sweat, are the tears. There's a lot of cultural metaphors for all these biofluids coming out from our body. They're actually very, very rich in analytes and biomarkers in understanding the body. However, they're typically unseen, right? So part of this was also to think about how we can be able to monitor and to visualize the unseen inside the body. Okay, and so one example work is called BioWeave. And so BioWeave is a thread-based sweat sensor that can be woven into these kinesio tape-like sweat sensing bandages. And they're woven with threads that are coated with the ability to sense these sweat analytes. And so we came up with two approaches of sensing. The first is the colorimetric sensing approach, which is a common optical technique. So by detecting different analytes, right, it would be able to change color to reflect the amount of what is being detected. And so here's an example of a under eye sweat sensing patch that can detect pH levels, change in pH levels, glucose, and also one's sweat rate. Okay, so for example, throughout the day, sometimes we might have some biofluids coming out from the corners of our eye, et cetera. It will then be able to collect that and to inform the person or the people around them of the sweat sensing analyte data. Another approach, another sensing approach is called electrochemical sensing. So this detects a change in electric potential to detect sweat changes. Okay, and we can see here a quick overview of the fabrication method. And here's a hybrid sweat sensors using both the electrochemical and the colorimetric approach. So we can see that the device that's on the forehead, which is an area with a lot of sweat, as we all might have experienced, right? This is colorimetric. However, behind the ear, there is the electrochemical electrodes also working in place to be able to detect both of these type of sensory values. And I think what was very important for us is to think about how we can sense sweat on a wide range of body locations, right? So there is a lot of sweat sensing research from material science. However, most of it focuses on, I like to call the golden location for smartwatch and all wearables because it's flat, like our forearm, the wrist. We're very interested in being able to take advantage of the structures of, especially in this project, woven textiles, to be able to create these patches are inherently conformable to much more diverse body locations. I'm just showing some of the examples here. In this next project, also detecting in-skin biofluids, we were inspired by the cultural body craft form of skin support patches. Who here has worn pimple patches? Very good, so many people. I see some of the the dudes also raising their hands. Very good. Okay, so the way that these pimple patches work is that they actually, this is kind of gross, but they're actually sucking stuff out from your pimple into the patch. So it is actually a microfluidic device. Okay, and so kind of inspired by this, and we can also see how a lot of these skin support patches, they're now also designed to be very decorative. At least I see a lot of my undergraduate Gen Z students wearing pimple patches in star shapes, heart shapes, etc. So yeah, I see some of the millennials in the room are like, I've never seen that before. I also just learned this from them, but this is kind of the inspiration for sweat skin. So sweat skin, it is also, we're taking inspiration from using a microfluidic approach for sweat sensing. And this fabrication process, we made it very accessible. So there are a couple of fabrication methods, but the intent is really you could do this from home using very accessible materials, right? And so here are some examples of some of these devices, right? So by absorbing sweat, if we look at the top right, you can see this balloon going from orange to like green to detect the pH levels, et cetera. And this coffee cup, when it's detecting higher sweat rate, this coffee turning brown, et cetera. And so it is using a more colorimetric approach and also the approach of microfluidics. And we contributed to fabrication processes. One is paper-based, so you can actually fabricate these devices using paper. Right. The other is polymer approach, which is also, and both of them can afford different types of specific modalities. And we really think by being able, right, to allow individuals, right, to customize these sweat sensing devices, we see a lot of potential for customizable health monitoring. So we're very excited about this line of work, being able to, I think, understand and visualize more of what is unseen in the human body. So the second set of hybrid skins that I would like to talk about next are what I like to call close body robotic textiles. And the projects that we just talked about, now they typically come in a layered form, right? Stack layers of very thin silicone. And at some point, it just became very clear to me that there are certain inherent limitations, right, to this layered and stacked structure. And this is what got me very interested in understanding and working with textile structures, such as weaving and knitting. So compared to these on-skin overlays, the way that they're typically fabricated is very thin layers of structures stacked, right? In woven and knit structures, you are actually constructing a two-dimensional, here our clothing, two-dimensional structure, right, from a one-dimensional piece of yarn, right? So you can really control the structure, right, in which the two-dimensional interface is created, right, by manipulating the construction through the one-dimensional yarn. And that became very fascinating to me. And so this got me in a very deep hole of wanting to purchase a lot of very expensive looms and Shimaseki knitting machines, etc. But I think it has also just been very, very and highly interesting. And so if we first look at woven structures, so woven structures typically consist of a horizontal and a vertical two sets of yarns at a right angle, and they have the quality of being inherently very stable. So I think, so raise your hand if you're wearing jeans here today. So I think most of us are, right? And so our jeans are actually constructed through a woven structure. This is why they're not like, like falling apart. And so Woven Probe was one of our early projects and our early forays into examining the potential, right, of weaving to create these, I like to call close body textile on-skin systems. And while we are using the textile techniques of weaving or knitting, the interfaces that we like to construct are still situated directly on the skin. So I like to think of them as more as skin bandages or patches, right? So woven textiles that are also situated on the body surface and can be attached to the body surface. And so in Woven Probe, we were interested in thinking of how we could began an early exploration into a self-powered on-skin sensing hand gesture interface, right? And you can see here that, let me try and play this video. So you can see here that this is like an early prototype. We have a NFC coil here that is able to harvest energy from this smartwatch like setup to enable the gesture detection on the wearer's fingers. And this entire interface that is worn is woven in one structure, right? And what became very interesting for us is understanding the richness of a lot of these culturally inspired structures that were maybe adopted in historically in woven practices for weaving quilts or blankets and clothing, but to apply them now for weaving these on-skin interfaces. So some woven structures that are culturally inspired that we adopted, one includes the lace serpentine weave. This is a hand manipulated weave in a serpentine pattern, and we employ them across the finger joints so that it is much more flexible, right? And in pattern, we can also see the serpentine patterning also adopted a lot in a lot of epidermal electronics, more of the printed works. Another very important weaving technique is Manhattan routing, right? And weaving, just because of its grid-like structure, it can afford this very well. So this really enabled us to be able to fully integrate these very miniaturized hardware components into the textile structure. So there are, I think, around I believe 8 to 9, I think, miniaturized PCB islands, right? And it is the routing afforded by the woven structure that also enables this. We also experimented with some more complex circuit topologies through double weave. So double weave is when you're weaving 2 layers of cloth at the same time, right? We use this to actually weave the NFC coil that is enabling some of the wireless charging through the smartwatch-like device. And so this was, I think it just really opened our eyes to, I think, a lot of the potential in learning from these historical woven structures, but applying them in new ways, right, to enable on-body applications. And so in Woven Probe, the prior project, we were mostly weaving with very, very thin conductors, right? So creating and connecting them to sensors. And we then got very interested in what if we could weave with yarn-like actuators, right? So in this project called Patch-O, we got very interested in weaving shape memory alloy actuators, patterning them into woven structures. And based on the different ways, right, in which they are integrated, when these shape memory alloy actuators are heated and actuated, they can enable a range of different forms of shape change. And you can see here some examples of some projects that were created by individuals who use this approach. We were also very just intrigued by the form factor of patches, right? So we know that patches is a cultural form factor that can be reused, right? And so we're also interested in having these shape-changing patches as a platform, right? So for instance, you could attach this to different body locations to enable different types of shape change. And so next, I would like to talk about some of our projects looking at knit structures to construct these on-skin patches. So knits are highly interesting. And so what enables a knit is it is essentially you're doing a loop-by-loop structure with one thread. And because it is consists of a loop-like structure, it is inherently very stretchable and also highly compliant, right? And so here I'm showing a image of a knit pavilion created by Zaha Hadid Architects in collaboration with ETH Zurich. So I think this is just an example of just the compliance, stretchability, and extensibility of the knit structure, right? And also knitting manufacturing and textile manufacturing in general can enable structures at much larger scales, right? So while my lab's work focuses on the body scale, there is also, I think, a lot of potential for it to even go on the interior or architectural scale, as we can see here. One of our early investigations in this space is called knit dermis. So we were very interested in how we can take advantage of the ability, right, of knit structures that they can contract and they're very stretchable. So we developed various knit structures, right, that can enable these channels, these tubular jacquard channels into the woven structure, and also several 2D and also 3D shaping techniques, right? So we can create these patches that are inherently conformable to challenging body locations with curvature, such as our knuckles, as we can see here. And much more underexplored body locations. And so inside these channels, they're patterned with shape memory alloy springs. And by attaching them to the body and based on the patterning, they can generate an array of tactile feedback. And from, for example, brushing, as we can see here, to compression. This is another example of compression. And also twisting, etc. And so I really just, and this is one of my favorite for pinching. You could also put it on your back, maybe for therapeutic massage, etc. And so kind of continuing this line of work in this next project, Knit Skin, we're interested to take these movement based robotic textiles to the next level, and especially thinking about how we might be able to create a knitted patch that is able to locomote, to move on the human body, right? And so in this project, Knit Skin, we were actually very inspired by how snakes can move, right? So snakes, they move without legs, and what enables them to do this is actually the scaling on the snake's end that enables them to have directional friction and to move in one direction. And so we essentially, you can see here our inspiration, the snake skin. We essentially replicated through bioinspiration a knit structural approach mimicking the unique patterning, the scale patterning of snakeskin. And by doing so, and then this interface, when it was locomoting these sleeves, they were then able to locomote in one direction and to also defy gravity and moving in that direction. So you can essentially think of it as the skin of a snake turned inside out. And because of the directional friction, it can now have with the cylindrical body, it can now move up. And so we also did a range of applications such as for digital agriculture, of course, on-body applications and therapeutic rehab, and also for urban infrastructure such as pipe repair. So this is a example in which they're knitted with water-soluble thread. So when it reaches like a pipe leak, it can solidify and close up the pipe leak. So this was, I think, a very interesting investigation for us to also think about hybrid skins, right, that can go on different scales beside the human body. In this next project called Nadima, we wanted to take our research in these haptic robotic textiles in collaboration with medical experts, right, to kind of understand, because when we do a lot of our early user studies and actually trying these devices, we found that they had the benefits of being very lightweight. However, they could also provide a very rich number of haptic sensations. And so in this project called NIDGERMIS, this is a collaboration with the Weill Cornell Medical School's rehabilitation department. We're creating a robotic textile glove that can sequentially contract to mobilize edema fluid from the fingers and all the way back to the heart. And what is edema, right? So here we can see two hands from the same person. This hand on the right is suffering from edema, okay, so abnormal swelling of the hand. And current conventional treatment methods are either through pneumatic sleeves, as we can see here, but they're quite bulky, or the patient would need to go into a clinic, right, and receive manual massage from a physical therapist or occupational therapist, making it very inexpensive. And so we were aiming to provide a much more personalized approach to enable participants to then take one of these gloves, right? And they could then receive treatment from the comfort of their own home. So thinking about the potential of robotic textiles for health equity. And I think in the final part of my talk, I would like to, I think, just, take a step back and also to think about, right, what does it mean, right, to design these type of interfaces? And what are some very important issues, I think, also for us to think about in the creation of these type of conformable on-body devices? I'll first start by talking about how democratizing the making of these skins, right? So how can we enable others, right, beyond those who have access, like we all do in this room, to advanced facilities, right, to also have a voice in deciding where the future of body conformable wearables are heading. So in like the early 2010s, when I started to work on these smart tattoos, I started to get a lot of emails from people who read some of our research papers, and they essentially replicated what we did in the paper, and they created their own on-skin interfaces. And I just thought it was very, very interesting. And especially if you look at this is actually some elementary school students from the Stewart Elementary School. So they created this on-skin selfie button, which I still think is quite hilarious. And in 2020, when I was shortly after I began at Cornell, I created a course on fabricating on-skin interfaces. So in this course, I would take some of our lab's research papers and to distill them into more digestible labs. However, in 2020, there was a global pandemic. And so this course was actually offered online. And so in this process of online teaching, hands-on on-skin prototyping, it also became a really interesting research experiment for me to understand how to make this process of constructing on-skin interfaces much more streamlined. And I think feedback that I received from my students in this course and also from these people who just read our papers and created these devices was that it would be very helpful to have a much more modular kit to make it even easier, right, to get started, to construct something very quickly. And so Skin Kit is one of our lab's early works in creating a construction kit for on-skin interface prototyping. So essentially, we're trying to create Legos, but for smart tattoos. So what if just by sticking together a couple of skin conformable, you can think of them as smart tattoo like wire modules, and then adding on the appropriate sensor and actuator modules that you would like, how can we enable this fabrication process of creating a smart tattoo to maybe be under half an hour was really our goal. So this skin kit at first consists of skin conformable wire modules. So by sticking these together, it really creates a substrate for then placing these PCB, the sensor and actuator modules on the skin. And I'll just very quickly show here an example of someone building a circuit with Skin Kit. And so you can see that they, first of all, they're selecting the sensors, um, modifiers, and actuators to use in their toolkit. So they tested that it works. Right. And next, what they're doing here is they're adjusting the layout, right, of this device um, so that it can be conformable and suitable for the specific body location that they are hoping to wear this one. And then we use a tessellated approach so that it's very quick to actually connect these devices together, right? And then we can see them now actually applying it on the skin. So yeah, very quickly you can have a proximity sensing LED tattoo. Um, we did a lot of workshops with college level students from engineering and design, and they were all able to create a wide range of devices in, I would say, around 45 minutes. Um, this also got us very interested in the potential, right, of using these kits for STEM learning. So in collaboration with the 4-H Youth Development Program and also our Science Center, we were able to bring these kits into the hands of middle school students. And they were also able to create these smart tattoo interfaces, I would say in within an hour. And so we can see that with Skin Kit, it does, while it's very quick to fabricate, it does have a larger surface area. And then we do observe the need, right, for certain types of makers, for example, on-body designers, makeup artists who want to put circuitry on the skin. However, they want to do it with much less surface area. And so this next project called Skin Link is a much more streamlined prototyping kit, and it also enables direct on-body manipulation and reconfiguration, right? And we're also using a more centralized circuit structure so that every sensor actually is connected back to this main module. So this is just a proof of concept of the 14 modules in our first prototype. And very importantly, what is connecting each of these miniaturized PCB islands are these stretchable wire modules, right? And so they, just by connecting them together and based on the way they're designed, you can very easily create much more complex circuitry with smaller surface areas. So we did a series of collaborations with for instance, this is a collaboration with a makeup artist where she used Skin Kit and to pair it with her own artistic makeup examples. And they're able to very also quickly prototype something much more streamlined in a limited amount of time. And this is another example with a special effects makeup artist. So we can see how in this example, they chose to completely hide the device under the special effects makeup silicone, right? And this is, these two projects both have to do with facilitating touch in the time of COVID. And so I think also a very interesting and important topic for us to think about in designing these hybrid skins is how can we design for sustainabilities, right? So I think conformable interfaces are very interesting in that they have a hardware component, the electronics, and also the conformable substrate. And e-textiles in general, they also connect these two most polluting industries, right, of our hardware circuitry, PCB, e-waste, right? However, also with the textile waste together. And so I just think in designing these hybrid skins, my students and we started to really think about how we can create a more sustainable life cycle for e-textiles and also conformable interfaces. So really thinking about biodegradability as a very critical and important design consideration, right, in what we're using to design something like this. And so in this next project called Echo Threads, we created a fabrication approach to essentially fabricate these e-textile threads that are biodegradable. And we can see here that the materials are all food and kitchen safe. So again, this is something that one could do in a very accessible manner. And then we wanted to enable this because a lot of e-textile practitioners actually do e-textile craft from the comfort of their own homes, right? And so through this fabrication approach, these threads, they're able to be integrated with common, like, textile structuring techniques such as weaving, knitting, embroidery, etc. And so this was a very interesting, I think, experiment for us to really focus on these biodegradable and also transient interfaces, and also to think about applications, right, in which it makes sense for a device to be transient, right? So after you use it, you can then let it biodegrade, right? But in a much more environmental sense friendly manner. And one thing that we did was because in the e-textile prototyping process, being able to prototype a lot of swatches to test what you're making is very important. So we shipped these biodegradable threads to e-textile practitioners. And here are just some examples of the projects that they were able to create and integrate into their existing textile practices using the yarns that we had. And so, of course, beyond thinking about the biodegradability, right, of the materials that we're using to create these devices, the power is also a very critical issue, right? And so LiPo batteries that are used to power almost all of the wearable devices today, they consist of a lot of toxic minerals. We're also very interested in thinking about how we can move towards self-powered sensors and also wearable devices. And so in this project called Skinergy, we're interested in using the triboelectric effect for creating a self-powered sensor. And so the triboelectric effect is basically, sometimes in winter when you touch the rug or something, touch your sweater, and then you touch the door handle, you'll feel like, an electric shock. That is the triboelectric effect, okay? And so we're basically using, it happens when there's a more positive and negative material, and when they're pushed closely together, it can generate energy. And so we basically developed a fabrication approach, embroidery-based, to create these self-sensing sensors. And they can do self-sensing in terms of, as we can see here, discrete touch detection, gesture recognition, and also, for much more discrete body locations as well. In our work, we really, I think, also benefit from being able to work in a transdisciplinary manner, right? And so I think in our research group, we have the opportunity to collaborate with a lot of folks coming from different disciplines. We also really like to engage with folks outside of the main research area. And this is just one example, collaboration with a streetwear fashion designer, Christopher Bevins. And so he was very interested in thinking about using our smart tattoos, the NFC tattoos, for his fashion runway at New York Fashion Week. And so it was a very interactive runway. So the models would be wearing these tags on their bodies, and the audience could then take out their phones to read information from these tags and to understand how the clothing was designed. So I think it was a very interesting I would say, experiment for us to understand how the fashion industry would react to these emerging on-skin interfaces. And while publishing our projects in these main ACM computer science conferences is very important. However, the number of people who actually visit art museums is just incomparable. And so we also love to engage with museums and art institutions. I mean, this is an example of our work exhibited at the Centre Pompidou in Paris. And it was also very interesting for us to be able to understand, right, how the art world would react to the role of technology and how it is currently situated, right, in terms of the relationship with the human body. So I think I've had the opportunity to collaborate with a lot of experts in on-body design, from apparel designers, fiber artists, fashion designers. And this really became a big motivation for setting up a artist residency in the hybrid body lab. And so in this artist residency, we're especially interested in inviting individuals who are experts in working on the body surface, such as tattoo artists, makeup artists, fashion designers, nail artists, hair artists, etc. And I just really think they have a very important role in teaching us as HCI researchers on what we should, but also should not do in terms of designing for the body. And so here is our 2022 artist in residence, Morgan Chen. This is a photo of her wearing her own makeup artwork, and she created a very interesting project called Social Prostheses that's really examining the role of beauty and also proximity directly on the face. Our artist last year was Joe George. So he is a multidisciplinary tattoo artist based in Brooklyn. I highly encourage you to follow his Instagram. He's like a minor celebrity there. And so we also learn a lot from George and Joe George, and this is his project. So he created this UV environmental sensing human snake skin that can basically change color to indicate elevated levels of UV. And I think these artists in residencies are just so important for our research practice and really being able to kind of shake up the boat a little bit and and to really change, right, the way that we are approaching things and learning from these artists. And this year, we're also having another call, and we're hoping to be able to invite a nail artist or hair artist. And last but not least, in designing for the body, I think it's very important to think about how we can move towards inclusive design. And so when I got started in creating these smart tattoos, like almost a decade ago now, I was trying to find mannequin arms of different skin tones to put these tattoos on because I wanted to understand how they would look on people of different skin tones. However, at that place and time, I could only find mannequin arms of one skin tone. So the arms you see here are actually those that I developed an approach to color them so that when I was doing a demonstration, I could always demonstrate these smart tattoos on a range of skin tones. And if we think about this, in the cosmetic industry, there's also been an increased, I think, awareness, right? And thinking about foundation colors, right? How can we create foundation colors that are much more inclusive and diverse, right? And so I think for technology that's also moving on the body, I think it is just so important also for us to be sensitive to and attuned to these concerns and thinking about how we can be more inclusive, right, in our approach. And in thinking about a lot of these problems, this next project and final project I'd like to talk about is trying to examine cross-cultural perspectives towards wearing smart tattoos, okay? And so we did a large-scale study from participants in the US and participants in Taiwan, so like a representative, like East Asian culture. And I'll just share one result, but what we found like very interesting distinctly was on preferred body location, right? So we asked people if today you had a on-skin touch sensor, where would you like to wear it? The US participants, almost 40% would prefer to wear it here on the outer arm. And we know that this is a quite common tattoo location for like the rose tattoo, these like, culturally significant tattoo decorations, right? However, in Taiwan, the inner forearm was the most preferred location, and because it was discreet, right? So the folks in Taiwanese folks, they said that, I want to have a smart tattoo because it's cool, functional, it can express my identity. However, when I'm meeting with my in-laws, right? Or if I'm at work, I want to be able to cover it, right? So we can see how, especially when technology moves on the body, there are just a lot of very important cultural sensitivities that I think we need to be aware of, especially in thinking about their long-term adoption. And so today, in presenting and sharing with you all a couple of our different approaches towards designing hybrid skins, I really hope to, just share a lens in thinking about the next generation of conformable on-body devices, how we can create them with greater reference to cultural and social concerns. And I think the goal is really to, let's say, in 50 or 100 years from now, the technologies that are on or even going inside our body, they can really enable and the expression, right, the full expression of who we are as individuals, and instead of constricting that to only a couple possibilities. And so last but not least, I want to definitely acknowledge my fantastic Hybrid Body Lab members, our collaborators. This is just a representative list, and also our sponsors supporting our work. And so thank you all very much. I'm happy to take questions.
So I know that we're at time, so like if people have to leave, I want to give you the opportunity to gracefully do so right now. But otherwise, we'll try to extend maybe for like 5.
Yeah, not a problem.
So the first question from the Q&A is from Maciek, who says, "Fascinating talk. Are your designs available as Gerber files anywhere so
Yes.
people can modify them?"
Yes. So I think if you go to our lab website right over here under tutorials, we have a lot of tutorials for creating these on-skin interfaces. Yeah, and also with files attached. So that would be a good place to start. Yeah, great question.
So great talk. Was so cool seeing all the demos. So thanks so much. One question that I have is, by working inside of this space where you're working with these embodied interfaces, I mean, not just embodied interfaces, but like literally on the body.
Right.
Obviously, some of these things that you're saying about like how personal they are, how they encode the information about how you want to present. All of these things are very different than you just have like a photo.
Yes.
I'm curious what you have learned about how people like to interact with these interfaces. Like, do they develop like different action patterns? Kind of what is kind of that cognitive side of how they actually interact with these interfaces? And how is that different on these types of like hybrid skins versus something like movable devices?
Yeah, that's a great question. And so I think I'll just repeat the question. I'm sorry, I didn't catch your name. Dylan was asking, what is the difference of how people interact with devices that are, for example, like, on our smartphone versus when it's directly on the skin? Is that correct? Yes. So if you just think about it, there are certain body locations, especially if we think about touch sensing, that are not culturally appropriate to be touching in certain public versus private settings. Okay. And so social acceptance becomes very, very critical, I think, in designing these on-body devices, right? And also the social meaning, right, of touching certain body locations. Some of it, it needs to be very carefully designed, right? So for instance, sometimes when we see someone, I don't know, like nervously twitching or touching their head, it can mean they're nervous, right? But then what does it mean? Because this may be, if we think about it from an engineering standpoint, this finger location might be a very good place to place a touch sensor, right? So then I think as designers and engineers, right, for us to think about then how do we design that gesture in a way that is still convenient, right, but is still mindful, right, of these cultural connotations. Yeah, and so I think there is a lot of more and more research in the wearable computing space looking at what they call social acceptability, social perceptions towards these devices. And I think it's just an especially critical factor for wearables. Yeah, because they're situated on the body. And it's just very tied up with cultural and social meaning. And today you can imagine, like in the US, it could mean one thing when you have certain hand gestures. But today, let's say you go to a different part of the world, it can mean something completely different, right? Or even sometimes something that is benign in one can become offensive, right? So I think it's very, very important, especially in the design of these devices, to be very careful about these concerns. Yeah, but that's a great question.
Yeah, so
Trying to remember the first big segment that I know of, it was 1998.
Yeah.
And the first industry, in fact, like, you know, like working people to look at your work, might have been like a mainstream and then you have already some idea of who that each kind of industry, that each company could use kind of application, could make your work in next week.
Yeah, that's a great question. So Cedric's question was how I might envision my work being used in real life, right? Maybe in 10 to 20 years. Yeah. Or maybe even faster, fingers crossed. Yeah, so I think the commercialization of e-textiles has been a challenge, right? Because I think the main challenge is that it's pairing together two industries, right? PCB manufacturing with textile industries, and they're both highly specialized. However, putting things together, the interconnects between the rigid and soft is very challenging, right? And there, of course, is more and more work looking into that, right? And I think another very big challenge for wearables is moving beyond the novelty factor, right? I think these devices, they all get a lot of attention when they're first on the market, but then long-term adoption becomes a very significant issue, right? And then in my lab's work, I think the approach that I would like to take, and because like, you know, I believe every one of us, more or less, we wear something, right, that is very strongly tied to that represents our identity, right? Whether it's our clothing, our jewelry, or for people who wear makeup or put products in their hair, etc. Right? This is something that this habitual practice is something that humans do every day. However, you can observe that it's highly unique to each individual, right? And then comparing this need for uniqueness and essentially more bottom up approach, right? And be able to construct, right, the things that are worn on the body from a wearable technology standpoint versus the current wearable industry, which is we have like, you know, certain categories of smartwatches. When you wear them, you have to conform, right, to the aesthetic, right? So I'm really interested in a future in which people would be able to wear these smart tattoos, these smart in-skin interfaces or textile interfaces in a way that really can reflect their identity, because I think that is the only way people will continue to wear them, right? It has to be adaptable to a person's identity as well. Especially in the stage of like globalization and like mass mobility, right? For instance, I dress very differently 10 years ago than I do now, right? And we might live in so many different cultures and be attuned to so many different communities throughout our lifetimes, right? But you have to design wearable technologies that can reflect that, right? And I think that is the real challenge. And this is why in my lab's approach, we like to create fabrication approaches that are very accessible. So the individual can have, I think, some level of agency, right, in deciding how this technology is not only going to look, but also what it can do, right? And also maybe to assign meaning into what it means, right, to now wear something like this. And today, maybe in like 5 to 10 years, their identity transforms or they change, right? Then they are also able to make that adjustment. Yeah, but I do think that is one of the most biggest challenges in thinking about wearable devices. So great question. Yeah.
It is now 5:10.
Okay.
Any other questions, please, come line up out, but in the meantime, please join me in thanking her.
Thank you. Thank you so much, everyone. It's a pleasure. So should I just, okay. And it's okay for me to just, okay, I'll just leave.